Hello friends, subscribers and new viewers of this channel, and welcome to Control Systems tutorial in Python. In this tutorial we explain how to define and simulate state space models in Python. In particular, in this tutorial we use Python and Python Control Systems library. We explain how to, number one, define a state space model, simulate and plot the step response of the state space model, simulate and plot the response to arbitrary inputs of a state space model, transform state space models to transfer functions and back, discretize state space models, investigate the dynamics properties of state space models and stability. But before we start with explanations, here is the copyright notice. This video lesson developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. This lesson and the provided material should not be used as lecture materials on online learning platforms and in university courses. This lesson and the provided material should not be used to train an AI algorithm or a large language model. Here is a brief illustrative overview of what you will learn in this video tutorial. Over here you can see a state space model with the system matrices given over here. This is a simple mass spring damper system. In this video tutorial you will learn how to simulate and plot the step response of this state space model. Here is the step response. The system is relatively well damped, and you can see that the settling time is approximately after 4 seconds. Over here you can see the response of the system to user-defined input. Here is the input that we constructed, and here is the response of the system. In addition to this, you will also learn how to investigate the dynamics properties of the state space model and how to convert the state space model from transfer functions back to state space models and vice versa. Before we start with explanations, we need to mention the following. This is the third tutorial in a tutorial series on control system analysis and design in Python. In the first tutorial, we explained how to install all the programs necessary to follow any tutorial in this tutorial series. Consequently, my advice is to watch the first tutorial. This tutorial will teach you how to install Python, Spider, and Anaconda. Consequently, in this tutorial, I assume that you have already installed all the programs. The idea over here is to create a workspace folder and to create a Python virtual environment. So let's do that. Over here, I'm going to move this document, and I will start a command prompt. So click here and search command prompt. Here it is. Let's resize this window. First of all, we need to create our workspace folder. Let's go to the base C drive and let's create a folder called Python Control. And let's navigate to that folder. Inside of this folder, we will create and activate a Python virtual environment. To do that, let's type python-m venv environment1. And after this, our Python virtual environment will be created. To see that, you will notice that in this folder there is this subfolder called environment1. This folder will contain all the packages and configuration files of our Python virtual environment. Next, let's activate the Python virtual environment. To activate the Python virtual environment, we need to execute the file called activate.bat inside of the scripts subfolder of the environment1 subfolder. And once you run this, you will see this environment1 written over here. This means that your virtual environment is activated. The next step is to install the necessary libraries. First of all, we need to install NumPy. So let's wait until NumPy is installed. This will take some time. Next, let's install matplotlib. Since we will plot graphs, pip install matplotlib. And finally, let's install the Python control systems library. To do that, we need to type pip install control. Besides installing the Python control systems library, this command will also install scipy. Now if you type pip list, you will see all the Python libraries and packages that are currently installed in our Python virtual environment. The next step is to start Spider. In this tutorial series, we are using Spider since it resembles MATLAB and it's very easy to debug Python files in Spider. So let's start Spider. Over here, I will run Spider as a standalone program. Of course, you can also run Spider by using Anaconda. To learn how to do that, you can watch our first tutorial. And over here, I will press cancel. Let me close this file. The first step is to make sure that Spider can recognize your virtual environment. To do that, first of all, you need to tell to Spider that we are using the Python interpreter inside of our virtual environment. To do that, you need to click on Tools, click on Preferences, and over here, click on Python interpreter. Then select this option, click over here, and locate the base folder of our virtual environment. Here it is. Then go inside of environments, go inside of scripts, and over here you will find this Python executable. And this is the Python interpreter that the Spider will use. Click on open, click OK. Now, you will see, for example, if you try to type something like this, import numpy as np, and if you try to execute this program, you will see something like this over here. This means that you need to install additional packages inside of your virtual environment such that Spider can use our virtual environment. And if you zoom here, you will see that this command needs to be executed. So let's copy this command and let's go to our virtual environment and let's run this command. This will install the necessary packages such that Spider can recognize our virtual environment. Okay, good. Next, let's go back to Spider and click here to close the current console, and the kernel will be automatically restarted and a new console will start. If you don't do it like that, you can also do it like this. You can simply click here on Restart the kernel and click on Yes. Another way to do that is to click here, then click on New Console. You can close this one and then you can do this. Console, restart the kernel. So there are many ways to restart the kernel and to start a new console. Good. Over here, to save time, I will simply paste this piece of code. The first step is to import the necessary libraries. First of all, we need to import plot from matplotlib.pyplot. This function will be used to plot graphs. Then we need to import our control systems library. Then we need to import numpy. Over here, I created a simple function that will plot graphs. Let's explain this function. Over here, we need to specify the time vector. Then, the second input parameter is the response vector. The third input argument is the title of the plot. This fourth input parameter is the x-axis label, the fifth one is the y-axis label, and the final input parameter is a string defining the file name. Namely, this function will plot the graph and it will also save the graph in a PNG or JPG file. Later on, I will explain how to use this function. Inside of this function, we define a figure, then we plot, then we add the title to our graph, then we add X and Y labels, then we adjust the size of the fonts, we introduce the grid, we save the file. Note over here that I'm using 600 dots per inch. My suggestion is to do that. Otherwise, if you use a lower resolution, for example 100 or 200, the graph will be blurred and the lines cannot be seen clearly. And this is especially important if you want to include these graphs in your scientific reports or in your papers. And finally, we plot the graph. That's it. Next, we explain how to define a state space model. Over here, I wrote the matrices from the example at the beginning of this video tutorial. The next step is to define these matrices in Python. To do that, we will use the NumPy library. And the matrices are simply implemented as NumPy matrices. So let's write A is equal to numpy.array, and we specify matrices like this. Over here, you need to specify the first row as a list. 0, 1, then comma, then next row, -4, -2. So let's use the same principle to define our matrix B. Again, let's do row-wise, 0 over here and 1 over here. Then let's define our C matrix. C matrix will again be numpy.array. Over here, we will have something that looks like this, 1, 0. And finally, let's define our D matrix. It will be simply numpy array, and then we will have this. And that's it. Let's verify that everything is okay. 0, 1, 0, 1, -4, -2, 0, 1, 1, 0, and D is 0. And that's it. To define our state space model, we will need to write sys state. This will be the state space model object that I will create. And to do that, we will use the function ct.ss. And over here as inputs, we need to provide the system matrices A, B, C, and D. Over here, let me explain this. I wrote ct.ss. If you go all the way up, you can see that we imported the control systems library as ct, and this is the suggested convention. Consequently, you need to type ct.ss. This is very important to keep in mind. Let's erase these matrices and let's continue. So here's why I like Spider. I can simply select a piece of code and then I can press F9, and over here I will evaluate everything. And you will see all the variables in your workspace, and you can simply even type whos to see, or actually whos, to see everything that is in the workspace or in the temporary debug memory. And here's our state space model. So we can type just this, select here and type F9, and here's our state space model. A, B, C, and D, or you can type print sys state. And here it is. You can see the inputs, outputs, and states. We have a single input, single output, and 2 states. And here you can see the system matrices. So let me copy this and put it here such that everything is nicely written. Okay, so now we know how to define a state space model in Python. The next step is to learn how to convert a state space model to transfer function, and how to convert a transfer function back to state space model. This is super easy. So let's type transfer function 1 is equal to ct, and then let's use this function ss standing for state space model, 2 standing for 2, tf standing for transfer function. And over here you need to specify the name of our state space model. So let's evaluate this, and let's now type here transfer function 1, and if you press enter you can see the transfer function corresponding to our state space model. Of course you can also type print over here and transfer function, and this will print a more primitive display of transfer function. Here it is. Now let's learn how to transform a transfer function back to the state space model. Let me call the new state space model as sysstate2, and we will use the function ct. Now over here we will type tf2ss, and over here we will specify the name of the transfer function. Here it is. Press F9 and let's see what happens now. Sysstate2, and let's compare this with sysstate, and here we are. We can see a difference. A, B, and C matrices are different. How is that possible? Are these different state space models? Well, they're not. These state space models are actually equivalent, and they're equivalent up to a similarity transformation. Namely, it's a very well-known fact in control theory that state space model representations are not unique. That is, there always exists a linear transformation of state variables that will transform coefficient matrices of state space models from one form to another. What is important to keep in mind that both of these state space models have the same input-output behavior, they have the same stability properties, such as the same eigenvalues and other stability properties, as well as the controllability and observability properties. The next step is to explain how to compute the step response. But before we do that, let's make a small adjustment. Notice this menu over here. This menu is the current working folder. We need to change this current working folder to our Python environment working folder. So click here, go to the C drive and click here on Python control and click on select folder. Good. To compute the step response, or better to say to simulate the step response, we first need to define the time vector for the simulation. Over here, I will be using NumPy linspace function. The start time will be 0, the end time will be, for example, 8 seconds, and in between I will have 150 time steps. To compute the step response, we need to use the function ct step underscore and then response. The first input parameter is our state space model, and the second input parameter is the time vector. Here it is. This function returns two things. First of all, it returns time. I will call this time returned. This is the time at which the samples of the step response are computed, and it also returns the actual step response. I will call it as system output. Good. Let's now select this and let's press F9 to evaluate. So let's see the output over here. What do we have over here? If I now select this and press F9, I will see my step response vector or array. And let's see time. Here is the time. The next step is to plot this step response. To do that, let's go back to the function and let's just copy this part over here. And let's fill in the input parameters. First of all, we need to specify the x-axis vector. In our case, this is time. So let's type time. Y-axis vector will be the system output. title string will be step response, the x-axis label will be time in seconds, and the y-axis label will be simply output. And let's give the name to the file. Let's call the file as stepresponse.png. Here it is. So let's select everything. Let's press F9. And over here, if you click on plots, you will see our step response. Looks beautiful. However, the step response file is actually saved in this folder, and let's inspect that file by going to this folder, clicking here, and here is the PNG file. And you can include this PNG file in your scientific report or in some other document. Next, we explain how to simulate the system response to a specific input. Again, the first step is to define the time vector. I will call it as time vector 2, and let's again use numpy linspace, and over here let's specify start time 0 and time 20 in between 400 time steps, and let's define our input vector over here. Let's type input vector 2, and let's, for example, assume a harmonic function. That will be a sum of sine, cosine, and a simple offset function. So let's write numpy sine 2 times time vector 2. Then let's add a cosine term. For example, let's do plus 2 times numpy dot cosine, and let's select a lower frequency, for example 0.5, multiplying time vector 2, and let's over here add a simple offset. I'll type this numpy dot once, and over here I will simply type this time vector 2 dot shape, and here it is. Next, let's plot this input vector. For that purpose, let's again go to the prototype of our plotting function, and let's fill in the entries. Over here on the x-axis we will have time vector 2, on the y-axis we will have input vector 2, title will be input, on the x-axis we will have time measured in seconds, on the y-axis we will have simply input, and let's save the plot as input.png. Now let's select this thing, press F9, and let's see our input. Here it is. Let's go back to the file, and here's the input. Beautiful. To simulate a state space response to this particular input, we need to specify the initial state. So let's set the initial state to be numpy.array, and over here, since the system is of the second order, we need to specify x01 and x02. x01 let it be 0, and x02 let it be 0. Over here you can change the initial state later on. Now, the next step is to simulate the state space response. To simulate the state space response, we need to use the function ct.force_response. And over here, as the first input parameter of the force response, we need to specify our state space model. The name of the state space model is sysstate. The second input parameter is the time vector. And the third input parameter is the actual input vector. Here it is. This function will return two things. First of all, it will return time returned, and it will also return system output 2. And let's call this time not time returned. Let's call it, for example, time returned 2, in order to distinguish this from other time vectors. And that's it. Let's now evaluate this, and let's see what happens over here. Now, if I simply select system output 2 and press F9, we can see our system output to the particular input. The next step is to plot this system output. To do that, let's go here and copy the plotting function, put it over here, and let's fill in the entries. The first entry will be time returned. The second entry is the system output 2. Title will be response. Let's specify the X label as time, Y label as output, and let's save this file as forced response.png. And let's now evaluate this, and voila, here it is. This is the forced response of the system. Now if you go back to our base folder, we can see the response of the system, and we can see the input of the system. Looks beautiful. Next, we explain how to obtain the basic information about the state space model and the step response. First of all, let's obtain basic information about the step response, such as the settling time, rise time, and other step response characteristics. So let's type step info data, and over here I will type CT, then I will call the function step info, and I will specify the name of my state space model. The name is sysstate. And let's see the output. Now if you type this thing, you will see the rise time, settling minimum, settling maximum, overshoot, undershoot, peak time, and the steady state value. Very useful information. Next, let's learn how to obtain information about the natural frequency, damping ratio, and poles of the system. To do that, you need to call the function ctDamp. And over here, you need to specify the state space model. And let's do this, do print true. And let's see the output over here. And over here, you will see very interesting things. You can see the eigenvalues or the poles, you can see the damping and the natural and damped frequency at that pole. Very useful information. Of course, we can see that the system is stable. However, we can also compute the poles by typing ct.poles. And over here, you need to just specify your state space model. And here they are. Here are the poles or the eigenvalues of the matrix A. Let's see the zeros if you have any zero. And over here you need to specify the state space. We don't have any zero. Next, let's obtain the pole zero map plot. To do that, we need to use this function ctpzmap. Let's select this and let's evaluate it. And over here you will see the plot. Now you can save this plot by simply do right click, save plot as, and let's go to our workspace folder and let's save it as pzplot. Here it is. Now you will have it inside of our folder and you can access it later on. Okay, so let's continue. Next, if you're used to MATLAB, MATLAB has a tool called single input, single output tool. Similarly, Python controls system library has the same tool. So let's type ct syso or syso tool. And over here we need to specify the name of our state space model. And let's select this and let's evaluate it and let's see the output. Here it is. You can see the body plot, you can see the body phase plot, you can see the root locus, and you can see the step response. Of course, the scale over here is not good and this graph is not optimal. However, there are several tricks that can be used to improve this graph. Again, you can do the right click, You can click on Save Plot As, and you can save it in the folder such that you can use it later on. Next, we explain how to discretize the state space model. The first step is to define the discretization sampling time. I will use sample time of, for example, 0.1. And over here, to discretize the state space model, you need to use the function ct sample system. And what you need to specify is, first of all, the name of your continuous time state space model. Then you need to specify the sample time, and then you need to specify the discretization method. There are several types of discretization methods that are widely used in control system theory. Maybe the most popular one is zero-order hold. Zero-order hold assumes that the control inputs are constant in between the sampling steps. So let's assign the output of this function, and let's call the output as sys state discrete. Now, if you select this, or better to say evaluate everything, and if you click here and do a F9, you'll see the discrete time state space model. Here it is. The next question is how to extract the system matrices. So let's try first of all to do this, and let's type .a, and here's our system matrix A, here's our system matrix B, C, and D. And let me type it over here such that we know how to extract everything. Again, C and D. Here it is. Then there is another very useful function that can be called. You can simply type your name of your state space structure, and you can type .isDtime, and you will get the response true, which means this is a discrete time state space model.